So the purpose of this study was basically to see if you could create a dust monitoring camera for a lunar exploration site using commercial off-the-shelf parts. To this end, we basically modeled dust ejected by activities around a lunar exploration site, as shown in Figure A, and the resulting radiance using scattering properties for realistically shaped lunar dust grains from our scattering grid. This will be for activities such as astronauts walking, rover motion, in situ resource utilization, and the like, and for the quasi-steady state tenuous cloud you'd expect around an exploration site rather than the instantaneous plumes from individual disturbances. Our results showed that sensitive dust measurements for concentrations of less than 1 microgram per meter cubed are possible with a well-baffled conceptual commercial off-the-shelf sensor-based camera. This would be a low size, weight, and power solution that could be readily accommodated on every landed mission, such as a CLIPS lander as shown in Figure B, or an Artemis lander. Sensor responses modeled included examples with flight heritage, such as the Shimea booster cam or the PL1 sensor from LISICube, the Dark Companion spacecraft. Dust abundance is readily measurable, and minimum grain size can be constrained. This would enable monitoring of the local dust environment, including ejection and deposition rates. Next slide, please. We modeled radiance for 3 different grain shapes, as shown here, irregular prolate spheres and spheres, and used optics in the geometry as shown in the figure at the bottom, where epsilon is the elevation angle. And did this for an integration time of 1 second. We then basically set the sun at an angle of 4 degrees above the horizon in line with a polar exploration site, and then modeled the signal to noise ratio for a dust line of sight and how that varies with elevation through the cloud. Shown in the top right are the results for the LISICube PL1 sensor-based camera, where the solid lines basically show you the signal to noise ratio for the baseline model, and the dashed lines show you the case where the dust concentration is being increased by a factor of 10. The thick dashed line through the middle is basically the signal to noise ratio equals 3 threshold, above which dust properties are confidently constrained. As you can see for the baseline model, that goes to angles over 30 degrees, and for the times 10 model for over 60 degrees. You can increase sensitivity basically by increasing integration time, sensor gain, etc. Also shown is zodiacal light in the background is the faint green line, which is a potential interference source, but also a potential calibration source. Some just grain shape differences can be seen, but polarization would tell us more. But if you want to know more about this, please read our paper published last year in PSJ by scanning the QR code. Thank you very much for listening.